In this video, we continue our work on optimization, second derivatives, and concavity. So let's take a look at example 4 on our first page here. So now the question asks, for each of the following functions, find the absolute maximum and absolute minimum over the specific interval and state where those values occur. So in the previous problems, we looked for local minimum and maximums. So if you just looked a little bit to the left or right of our critical point, does that point a maximum or a minimum? But whenever we're looking at our function over an interval, a closed interval, like the ones in the examples we'll see here, we can ask the question about a global or overall maximum or minimum. We're going to see some examples about how to do that in this video. So when we are looking for overall maxes or minimums, we want to first check critical points. So I'll make a note over here. This is called global or absolute maxes or mins. So global or absolute. We'll just call extrema. We use the word extrema whenever we want to refer to a maximum or a minimum, one or the other at an extreme value. So what do we need to do? We need to check critical values. Of f. Then we also need to check the endpoints of the interval. And by check, what do I mean by that? I mean determine, find which f of x is largest or smallest, if we want to find a min. So just to see why this makes sense, if we look at the graph that we saw in a previous video. So here we looked at critical values being the point -1 and 1. And we saw that in what we could see that this looks like a minimum on our graph here, and this critical value was a max. But what if I cut off my graph? I said, I don't want to look at everything on that interval. I'm only going to look at the graph from -1/2 to 2. So if I just take the snapshot, what do I see as the local minimum or a absolute minimum? Well, here on the edge is where my graph is the function value is the smallest. So here is where I have an absolute minimum. Notice again, my graph never goes below that output value. What about an overall maximum? Well, we can see an overall maximum right here. My function never gets larger than right here on this interval. So what we do in this situation, again, would be, to summarize, would be to find those critical points on that interval, identify those endpoints of our interval, in this case 2 and -1/2, and then ask the function, okay, of these values, what output value is largest and which is smallest? All right, so going back to our example, let's take a look in this first situation. So our function is written here. So in order to compute the critical values, we first want to find the derivative. So we want to compute f prime of x. So please take a moment and pause the video and compute the derivative before continuing. All right, when you're ready, let's check together. So derivative of -x² would be -2x. Derivative of 3x is just 3. Derivative of -2 is just 0. So here's our derivative. So critical points, we want to check for when 0 is equal to -2x plus 3. So here we're just finding critical points. So we'd solve for x here. So we'd have 2x is equal to 3. So dividing both sides by 2 tells us x is equal to 3/2. So here's one critical point. Does our derivative ever not exist? Nope, it always exists. So we're fine there. So our test points, where we're going to test for a max or a min, will be at the critical point, 3/2. So when x equals 3/2, and the endpoints. So when x equals 1, x equals 3. So just to emphasize here, these are from the endpoints of the interval. So we're testing these points on what function? Well, we're testing them on f of x. What we're going to do is determine at these 3 points that we've identified, what is the output value of f of x? From there, we will compare them and identify the largest and smallest, and that will be where our function is an overall or absolute max or min on that interval. So let's compute. So we want to take f of 3/2. So we go back to our function here to find that output value. So that would be negative 3/2 squared plus 3 times 3/2 minus 2. So what do we get when we compute that? Awesome, we should be getting 1/4. So now let's test when x is 1. So f of 1 would be negative 1 squared plus 3 times 1 minus 2, which is negative 1 squared, which is just negative 1, plus 3 minus 2, which is 0. And then finally, let's check f of 3. So that would be negative 3 squared plus 3 times 3 minus 2. So that becomes negative 9 plus 9 minus 2, which is negative 2. So now we have these 3 possible values that could be maxes or minimums for our graph. So of these, 1/4, 0, and 2, which is the largest number? Excellent, right here at 1/4. So this input value is going to be our max. And we'll say max occurs at this value of x. So the actual maximum value, the maximum output of our graph is here at 1/4. But where does it occur? When the input is 3/2. So now of these values, which is smallest? Right here at negative 2. So negative 2 is the minimum, and that minimum occurs at x equals 3. So now let's take a look at our function on a graph, and just to confirm that the absolute or global extrema are what they are on our graph. So let's go over to our Desmos calculator, and we're going to type in our original function. Negative x squared plus 3x minus 2. All right, so here's our original function, but recall we are on a specific interval. So we are only looking at x going from 1 to 3. So it's like we cut off our function and only looking at this part of it. So now we see that as we begin our graph, we're not quite at a minimum, right? At x equals 1. But then we go up all the way up to 1.5, which is input value of 3/2, and we see a maximum there. And then we decrease all the way to the endpoint of 3, where we get our minimum. So does this match the work that you just did? Awesome, it should. So the maximum value is 1/4. It occurs at 1.5 or 1.5 or 3/2, however you want to say it, all equivalent numbers. And the minimum occurs at the output value of negative 2, where the input value is 3. All right, feel free to draw this graph on your notes for future reference. All right, great work, everyone. Thanks for listening.